Hi class, welcome to the continuation of our lectures on electrodynamics, and this is the fourth one. And again, our main reference is Introduction to Electrodynamics by David J. Griffiths, and I recommend you to buy the book. So to continue, but by the way, before we start the fourth lecture, I'd like to go back to the other vector product with the del, which is the curl, and this is what I've told you in the last lecture, that it can be written in terms of matrix. The cross product of two vectors can be written as a matrix, as you can or as you have experienced before with two vectors A and B, for example. And this one is the expanded form. The geometrical interpretation is that when you have two vectors, when you have a curl of a vector, that means that the vector is curling in a source axis. So in this case, in figure 1.19a, you have an axis z where the source is located there, and the source of the curl, which is v, you have there some vectors curling the source. So it goes around the source. I'm drawing a spiral, but it's not actually a spiral. Here you also have the curl represented by this direction here, and then on this side it would be in that direction. So you had earlier for the curl of two vectors, but then you have a del and a vector function. You have to analogously write this. These are just analogous to each other. So in that example, you have VA equals negative y x hat plus x y hat, and then you also have VB x y hat. You can calculate their curls. So here you have x hat, y hat, z hat, and then partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then on this column you also have negative y, and in this column you have x, and since it has no component in the z, so you can just put there equal to 0. And so when you manipulate everything, you will get 2z hat. And for VB, you also have these ones. You have no x hat component and z hat component, so you only have z hat here. So just try to manipulate and you'll get the same answer. So now we'll go on to the rules on derivatives. So there's a sum rule. So you have two functions and you want to get the derivative of those two functions, then it's just equal to the sum of the derivatives. And if you have a function multiplied by constant k, so you will have you can take off the k out of the function, put it in front of the derivative. So it's a quite trivial rule. And then you have also the product rule here, which we have learned earlier in our academic life. And then you also have the quotient rule here. So anyway, the quotient rule is it's just written this way: df of g to the negative 1, and then you use this identity here. So this is just df times g to the negative 1 plus f times the derivative of g to the negative 1 is negative 1, so you can erase that and write negative here, g to the negative 2 dg. And so finally you have so you have df times g minus f so this is negative 1, sorry. And so this is g to negative to the negative 2 dg. So this is now equal to df times g over 2 minus f dg over g square. So you will have, so everything will be divided by g square, so you will have this finally. You will have this rule. So in similar fashion, the del also, the generalized derivative or the gradient, also follows the same rules. So if you have the del of or gradient of f plus g, that's just the sum of the gradients. And then when you get the dot product of a gradient to a plus b, then that's just the sum of the dot products. And also the cross product of the sum, is just the sum of the cross products as well. And if you have a function and you get the gradient of that function, that the function is and if the function is actually a product of a constant and another function, then you can just replace the constant outside and just get the del or the gradient of f. The same case here and also here. So there are two ways to construct a scalar as a product of two functions or as a dot product of two vectors. So we know this and we know that. And there's two ways to make a vector. You can multiply a vector to a vector function, and also you can cross a vector to another vector. These are also the product rules. derivative rules on products, or the gradient rules on products. You have, for gradients, you have this one. As you can see, it's just the same. And for the gradient of a product, this is the rule. You have the gradient of A dot B, then this is A cross del of cross del cross B, plus B cross del cross A, plus A dot del of B, del times B, plus B dot del times A. So this is the rule. And for the divergence, you have the divergence of F times vector A. Then this is also the rule for that. So it's just like doing the gradient of a product, but in this case you're actually doing a divergence. This is now the divergence of a curl. So this is backup rule, but one of the vectors there is just the del, but yeah. And then you also have for curls, you have the curl of F times vector A. This is also the simplification of that. Actually, it is a simplification, but it's actually longer than the original. And this one also, it's also the rule for the curl of the cross product. So here, if you investigate the divergence of F times A vector, this is just this one. So you have if you separate them by components, this is just a partial derivative with respect to x times F times AX, plus partial derivative with respect to y times F times AY, partial derivative with respect to z times F times AZ. And so if you expand this, you can actually expand it like this one here, expanding it in terms of the sum of the derivatives. And in similar fashion also, the second term is expanded to that, and the third term is also expanded this way. And so if you separate them, let's taking this one here, this one, and this one, you can write that like this here, and this one say this one, and this one, you can write it as the three of them. You can simplify that to that. So the quotient rule also is the same as the ordinary derivatives. So you get the derivative of the numerator times the denominator minus the derivative of the denominator divided times the numerator. You subtract it from the first, and then the denominator of them is just g square, and this one also, it's pretty the same. You just be mindful of this one and this one. And here, look here, it's positive because if you flip this, it will be negative, because you know the rule of A cross B is negative of B cross A. So that's it for the rules on gradient. And then we now go to the second derivatives. So we can apply the del twice. So if there's a need to apply the del twice, so here is a gradient of a vector. So if you get the divergence of a gradient, it would be like that. And so it will simplify to that. This one is actually just equal to over x partial derivative, second partial derivative of t with respect to y square, plus second partial derivative of t with respect to z square in component form. So the curl is this one, but let's maybe we can use the formula in the previous slide to get the equivalent for that. And this is the divergence, the gradient of the divergence, because the divergence, this one is it's not a vector, and you get the gradient of the vector, the gradient of the scalar, sorry. And this one is the gradient of the curl, it also exists. And the other one is the curl of the curl. So let us continue. You have the gradient of, the divergence of a gradient. First, you write the expanded form of the del, and then you have here the gradient of t. So this is like a vector product. A dot product of two vectors. So this will just be, but be careful because you are dotting an operator to another operator. So this does not mean square, but this does mean that you're taking the second order derivative. You're taking the derivative twice. Once you've taken the derivative the first time, you then get the subsequent derivative. You don't square it. By the way, we call this the Laplacian of t, denoted by that one. The Laplacian is a scalar. The Laplacian of a scalar t is a scalar. You can also get the Laplacian of a vector this way, but the Laplacian of a vector is also a vector. So you can write them in component form. Here, the curl of a gradient is always 0. Why is it always 0? Because you are the gradient of t is in the same direction as the del, so it's 0. In Cartesian coordinates, the unit vectors x hat, y hat, and z hat are constants. They have magnitudes of 1 and directed only in the x direction all the time for the x hat. For the y hat, it's only directed on the y all the time, and for the z, it's only directed on the z-axis. But if you go to curvilinear coordinates like spherical polar coordinates and cylindrical coordinates, you will see that the vectors, the unit vectors there is changing its direction at every point. There's no point that has the same direction. Unlike in XYZ space, the x hat, y hat, and z hat always points on the same direction. But the three coordinate system, XYZ, the r, rho, and theta, and the other one is r, theta, and z, they have their own advantages in solving problems. Later on, as we solve problems in electrodynamics, you will see that they have their own advantages depending on the symmetry of the figure that you are looking into. By the way, this is the product rule. This one here. And now, by the way, because you treat the x and y to be independent, so this is a valid identity. This one is the curl of the curl, and you can actually simplify that to just these to these two terms: the gradient of divergence and minus the Laplacian of vector function, where this one is just this one here. Now we've learned so much about the calculus of derivatives. Now we'll go to integral calculus. So we have three types of integral: the line integral, surface, and volume integrals. So this one is the first one, where you get the line integral of a vector function that dl. Here you can actually expand this to vx dx plus vy dy plus vz dz, this one here. So you can get the integral, and this is just an ordinary integral that we know in math. So you can perform this one, and this one, and then you add the three. That's just the path integral of a vector, or the line integral of a vector that dl. So here V is a vector function, dl is the infinitesimal displacement vector, and the integral is to be carried out along a prescribed path P from point A to point B. So you have an initial point and a final point. But of course, if you go from A and then you go back, so the final point and the initial point and the final point are the same, what could be the answer? The answer will actually be if your final point is equal to the initial point. It could be 0 or not 0. It will be 0 if your vector function there is conservative. It is not 0 if the vector function is not conservative. So this is how you geometrically represent the path integral, or the line integral, sorry. So line integral, you have a final point A and then initial point A and final point B. So the path here is specified by some curve, or you can also get from A to B this way. In this case, if from A to B using this path is the same as this one here, then that's called path independent. So if you use this path also and you get the same answer, it's path independent. Or if you use this path, so you can actually use other paths. So if you do a straight line, if you get the same answer as this one, then that is what we call path independent. And if it's path independent, meaning if you go around from A to some point and go back to A, the answer is always equal to 0. And that's what we call, and that actually implies that the V there, or the vector function, is a conservative vector function. So if you're getting a closed loop integral, you can write a circle in the integral here. So this means that when you go from A, you go back to A also. This is what it means here. So let's take an example. So you have a conservative vector if the integral is path independent. So whatever path you take from A to B, the answer is the same if you have a conservative vector function. So there are two, for example, here you have a force the force could be a friction or a weight, for example. The weight is a conservative force, but friction is not a conservative force. So friction is path dependent. That means when you take a path from A to B, you will have some friction there. And if you take another path which is longer than the original path that you have considered, then it will do a lot of work, because friction is a force that is converted to heat. So more heat will be produced in a longer path, and the shorter path would just give you smaller amount of heat produced. So it's path dependent. While for the weight, you have a weight here, and then if you transfer it to a higher place, the potential energy is increased. But if you take the object there, and you let it go, whatever path you take, you let it go back to its original position, the potential energy goes back to the same amount. So that it's what we call path independent. And so the weight there is a conservative vector or a conservative force. So let's take this example. Calculate the line integral of the function v equal to y square x hat plus 2x times y plus 1 y hat from point A 110 to point B 220 along paths 1 and 2 in figure 1.21. What is the closed integral of v dot dl for the loop that goes from A to B along 1 and along the path 2? So let's consider this path. So you have from, so this is just a two-dimensional problem. So you take the first path here. What is that? You go from in the xy coordinates, you go from 1 1 to 2 1, and then going from 2 1 you go up to here, then you go to 2 2. So you have two segments. You have two segments, 1 1 2 2 1, and then 2 2 2. In this path, for example, in 2 here, you go from 1 1 directly to 2 2. So let's do this example. So before we go to that, in this segment, your y is constant, and this is just equal to 1. For this segment, your x is constant, and this is just equal to 2. So now let's we are ready to solve the problem. So here, of course, in general, dl would be dxx hat plus dyy hat plus dzz hat. And path 1 consists of two parts along the horizontal, where dy equals dz equals 0. Here, only the x changes. Only x changes here. And the value of x starts from 1 to 2. So your v.dl is, of course, I think I've written it here, somewhere here earlier, or shall I or I'll just so anyway, integral of v dot dl is just equal to integral of vx dx plus integral of vy dy plus integral of vz dz. In the figure, we don't consider the z-axis, so it's constant on the z-axis, so this is automatically 0. And dy, y is constant, y is equal to 1. So y is equal to 1, y is equal to 1, so therefore if you get the derivative of y would just be 0. So this is also 0, so everything would be 0, so you only have vx dx. What is vx, by the way? So in this case, you have vx is y square. So you have v.dl equals y square dx. But what is y? Y is equal to 1, so y square will just be also equal to 1 square, so this is just equal to dx. So v so v.dl is equal to integral from 1 to 2, because you are going from 1 to 2 for the value of x. So this is just the value of so the integral of dx is just equal to x. This is just equal to x evaluated from 1 to 2, so this is just equal to 1, 2 minus 1, so equal to 1. And then for the vertical segment, this one here, for this segment, x is equal to 2. And your y runs from 1 to 2. Your x is equal to 2. And of course your z is also a constant in this case. But we don't care about the z. We only care about yx plane, because the path is on the xy plane. Now, so of course dx and dz is equal to 0. So we have dl is equal to dyy, because dx is equal to 0. All the other two component of the segment is 0. You have x is equal to 2, So v, in this case, you only have y, so you only look at this component here, and so to do that you have only 2x plus y1 dy. So since x is equal to 2, so this becomes 4 y plus 1 dy, and so your integral would be, so you take the 4 out, this is integral of y plus 1 dy. So this is just 4 times y square over 2 plus y, and you evaluate that from 1 to 2, and this is just equal to 10. So what is the total integral now? What is the total integral? So the total integral of the two segments, you have here the integral on this path is 1, and on this path is 10. So you have to add them. This is 1 plus 10, so this would be 11. So the answer would be 11 for that particular path. How about the second path? How about for this path here, only here? So neither x nor y are constant, but you have a relationship here. X is equal to y. So therefore, dx is equal to dy. And of course, as I've said, we didn't care about the z, so this is 0. So dl is just dx dy, because none of them is constant. And so your v, you have x squared dx, and then you have 2x x plus 1 dx also. Though the y here becomes x because x is equal to y, so you can write x instead. So finally, and also d is supposed to be dy here, but dy is also equal to dx, so you can write dx also, and then you can add the terms and you can simplify the expression to this, and now you get the integral. So this one is like 3x squared. The integral of that is x cubed, and this one here, the integral is x squared. Then you evaluate from 1 to 2, and then you will get 2 cubed is 8 plus 2 square is 4. This is equal to 12. If you have minus 1 plus 1, so everything will be just equal to 10. So what can you say about vector v? The integral is not path dependent. It's not path independent. It is path dependent, because when you use the other path, it gave you 11. This path gave you 10, so they are not equal. So the v there, since the integral is not path independent, the v is a non-conservative vector. So if you if you go around integrating the vector, from a to b, so if you go here to here and go back here, you have a result that is not equal to 0, and that result is just equal to the area of the enclosed figure, in this case a triangle. So your total integral closed loop is equal to 1. So that's about the line integral. Then we now go to the surface integral. So doing line integral was a little easy because you're dealing with simple integral. But here in surface integrals, you have a double integral. So the dA here, so V is a vector function, and the dA would be, so dA would be equal to d dy dz x hat plus d x dz y hat plus dx dy z hat. So those are the components of A. So in this case, you have, for the xy plane, for the xy plane, the dA is directed this way, which is perpendicular to the xy plane. For the xz plane, this would be your dA. And for the yz plane, this would be your dA. That's the direction. So in general, if you have a surface, the dA would be directed perpendicular to that surface. So in this case, the dA would be here, and in this case, the dA would be here. So it's different orientation at every point in a general surface, in a curved surface. But if you have a plane surface like xy plane, it's always directed on the z-axis, or for the yz plane, it's always directed on the x-axis. But you also have to be careful, because sometimes the problem would consider the direction of dA to be positive in this direction. Say for example, if this is outside, sometimes they consider that as positive, or most of the time they consider it as positive. If you have a closed surface, like a sphere, this one is positive, and this one here going inside is negative. So that's also what you have to be careful of when you solve problems later. So let's so if you're integrating over a closed surface like a balloon, then you have to put a circle here. So again, if you have if there are two directions, perpendicular to any surface, so the sign of the surface is integral. The sign of the surface integral is intrinsically ambiguous. If the surface is closed, forming a balloon, there's a circle on this integral here. Then the tradition dictates that outward is positive. But for open surface, it is arbitrary. So you can assign, for open surface, you can assign positive up or positive down. Depends on you. But for as long as you are consistent with it. So V describes the flow of a fluid, mass per unit area per unit time on the surface. So like if you have a surface here, then some fluid would go out there. So you can use this is the operation that you have to do. So if you have a surface here, a closed surface, for example, and the fluid passed through the surface, and also it goes out of the surface, the integral here is 0, since you have three fields going into the surface, and then it goes out in the same amount out of the surface. So the integral there is 0. But if you have a surface like this, if you have a surface like that, and you have so many going in and only a few go out, so the surface integral here is not equal to 0. So here's a note here. The value of a surface integral depends on the particular surface chosen. But there are also special class of vector functions for which the integral is independent of the surface, and it is only determined entirely by the boundary line. So there's also some kind of conservative V. That's the surface independent integral. So let's take this example. So for this example, you have calculate the surface integral of V with 2xz x hat plus x plus 2y hat, and z is equal to z square minus plus y times z square minus 3z hat over 5 sides, excluding the bottom of the cubical box, with side of 2 units. Let the upward and outward of the positive to be positive directions, and indicated by the arrows. So it's specified here that the direction of the surface directions are positive if it's going outside. So we have the x component of V, the y component of V, and the z component of V. So let's take the first side. Let's take one side at a time. So here you have for this one, we have this integral. So we're only doing the surface integral in the zy plane. In the zy plane, you only have this one for your dA. And so your VdA would just be equal to 2xz dy dz. But x in this case, for this plane, is equal to 2. So, I mean, that the x there. So your 2xz becomes 4z. And so if you integrate that, it will just give you 16. For the second surface, so let's look at the second surface. The second surface is this surface here. The x here is equal to 0. So your for that surface also, you're also again on the yz plane. So your x would be equal to 0 there, and your dA is equal to negative dy dz because the direction is going opposite to the x-axis. And then you have VdA is equal to negative 2xz dy dz because dA is negative. So and you actually the whole integral is equal to 0 because x is equal to 0. And then for the third one, you have y is equal to 2. The third one the third one is in this direction. So you're on the xz plane. So xz plane would give you, your dA would just be this one. So in the xz plane, your y is equal to 2 on this plane. Y is equal to 2. And so for y, you will have to use this one here. And if you take the integral of that, that's just equal to 12. You can manipulate the integral, see if you can get 12. And then for the fourth one, y is equal to 0 here on this plane, but it's also in the opposite direction. So your y is equal to 0 and dA is equal to negative dx dz y hat. But then your VdA is negative x plus 2 dy dz. So if you take the integral of that, that would be negative 12. And then for the last one, the z here, your z is equal to 2 in this case. And you have to use this also. You have to use this. So your dA would be this one, and that is your value of z. And then your VdA here, but z is equal to 2, so you can just write this as equal to 8. So anyway, this is just equal to so that will give you this is 2 square minus 3 is just equal to 1, so it will give you, it will simplify to this. And then finally you will have the integral of this b dot dA. So evidently, if you add the 5 surface integrals, it will give you 20. So this is for this session. I hope you've learned something, and in our synchronous class you can ask questions. That's all for now. So I hope that you'll be preparing your questions before we have the discussion. I mean, the question and answer part of the class. Thank you so much, and see you next time.